Good morning. Thank you for having us. Just as in a way of introduction, my name is Shmuel Kliger. I'm president and founder of VMTurbo. As Jonathan said, we started VMTurbo in 2009. Prior to that, I was a CTO at EMC. I came to EMC as part of an acquisition of the company called Smarts. I was CTO and member of the founding team of Smarts. We started Smarts in '93. We were the leading providers of root cause analysis for networks, and we were acquired by EMC for $285 million. Prior to that, I was a researcher at IBM TJ Watson. So why are we doing what we are doing? So if you look at IT operation for the last 2-3 decades, it's designed around this perpetual loop of collecting a lot of data, tons of data. If there is something moving out there in the IT, something that breeds something in the IT, there's probably a little tool that collects some data about this little thing. And we store this data, we analyze this data, we train this data, and we produce reports, alerts for some human to consume, telling us, in most cases, Houston, we have a problem. And then human look at this information, giving the tons of information that we collected for him, drilling down, navigating through this tons of information. And by the way, usually when we have a problem or something going wrong in the IT, we don't get a single message, oh, you have a problem, here is the problem. We built our previous company on exactly on that issue, that when a problem occurs in the environment, you're getting a flood of messages. Problems propagates through the IT, and tons of messages, hundreds of messages are coming out saying, oh, we have a problem. So a human has to go into a process of drilling down, navigating through this tons of information, troubleshooting, trying to figure out what is the actual problem that we have in the environment. And if he's figuring it out, fix it. With the sole purpose to bring it back to a healthy state, a desired state, a state the environment was to begin with. And by the way, as I mentioned, at each step of that loop, a lot of head scratching, a lot of finger pointing. It's a storage problem, it's a network problem, it's an application problem, a lot of running around. And furthermore, the heavy lifting, time-consuming, labor-intensive part of this loop take place when? When something wrong is happening in the environment. When someone is suffering, when applications are not getting the service that they need to get. So the fundamental question we are asking is why? Why are we accepting this design of IT operation? Why are we accepting this mode of operation of design to break and then fix? Show me another system that is designed like that. Are we ready to get on a plane that is designed to crash? No, but we are ready to run our mission critical application on IT that maybe won't deliver the service that it's supposed to deliver. And furthermore, there is a whole industry in the last 20, 30 years that feeds into this loop. Tons of money is being spent on monitoring and collection and reporting to show information, to show user more and more data, more and more information to keep him busy. Does that make sense? Can't we do better? Wouldn't it be better if instead of being busy with this break-fix loop, we'll figure out what is this good state, the desired state that the environment should be in, and in software, we're figuring out that state, and in software that continuously monitor, analyze, and act on the environment will drive and control the environment in that desired state. If we do that, operation will be smooth, service delivery will be smooth, service delivery will be predictable, and maybe we can relax. Now, the challenge is that in order to be able to do that, there is a fundamental problem that needs to be solved, the problem that we call the intelligent workload management problem. And I'll explain that problem in a second. And by the way, if we do it right, instead of having user interfaces like this, that looks like an ICU monitor that someone is about to die, we should be looking at those type of screens. Because if we do it right, we don't need human staring at screens. And if we do it right, we can have an industry that will try to figure out how to really operate IT, rather spending millions and millions of dollars on icons and trends and graphs. So now, let me explain what is this problem, the intelligent workload management problem, that needs to be solved in order to enable this transformation of IT operation. This problem we define as the problem of how to assure application performance while utilizing the environment as efficient as possible. This is plain English. How do I assure application performance while utilizing the environment as efficient as possible? The first, assure application performance, this is our main goal in life as an IT people. Our goal is to deliver service, making sure that the applications are getting what they need at any given point of time. Well, virtualization came around with the purpose of increased efficiencies, consolidation. If you go back, when we started in 2008, IDC published a report that there is 95% excess capacity worldwide in data centers. And that was equated in 2008 to $140 billion. That means that if round number, that means that 1% utilization is equated to $1.4 billion. So virtualization came along with this purpose to take advantage of this excess capacity and increase utilization. So the entire game, if you want, of virtualization is how to assure performance while utilizing the environment as efficient as possible. Now, I'm pretty sure I don't have to elaborate why this problem is important, why solving this problem is important. If I don't assure performance, there is direct implication on revenue. If I don't run the environment efficiency, I spend too much money. If I do it the old way, with this labor-intensive ad hoc manner trying to react, I'm spending too much labor. Now, this turns out that this problem is not so simple. It's actually very complex. Solving this problem of how to assure application performance while utilizing the environment as efficient as possible is very complex, because in any decent sized environment, if you have, let's say, 5,000 virtual machines, there is a lot of moving parts. And there is a lot of resources, metrics, knobs that you, as an operation, needs to be considered at any given point of time. Let's do a simple arithmetic. If all we care about virtual machines is about their VMem, vCPU, the ready queue, the vStorage, we care about their averages, the peaks, you very quickly gets to something around 10 to 20 different metrics that you need to consider to be able to figure out what's the answer. And if you have 5,000 VMs, 5,000 times 20, that's 100,000. Add to that the data store, add to that the host, add to that the filers, the aggregators, whatever you have in IT. There's a lot of moving parts. You very quickly get to hundreds of thousands of metrics that you have to consider continuously to figure out what is this desired state in which application performance are assured while the environment is utilized as efficient as possible. And now, the key to remember is that you cannot make those decisions and figure out what is this state by looking at a single matrix. You cannot just say, oh, this VM, I look at its CPU and its vCPU is very busy, and instead of 2 CPUs, I'll give it 4 CPUs and life will be good. Because it depends. Depends what's the ready queue on the 4 CPU at that time, depends what the other VMs are doing, depends on the underlying host, depends on the storage that they are sharing. So you cannot look at a single variable and drive a decision. In fact, we can go to different use cases and illustrate that by reacting to a single variable, you can get the environment to a worse state that it was before any change that you are making. So this is a very complex problem. Furthermore, the nature of workloads that it's fluctuating. So if I'm a human and I give you all the data in the world, and you look at all the trends and reports and alerts that I can give you, by the time you'll figure out what is the state that the environment needs to do and what do I need to do in order to get to that state, everything changed. So this problem cannot be solved by a human receiving data, collecting data, or looking at trends and trying to figure out what to do with this information. That has to be solved in software. Let me dive in a little bit and explain what does it mean to solve this problem. And before explaining what is a desired state, let me talk about what is a state of the environment. So, for example, if you have one host in the environment and all you care is about the memory of the host. So if someone comes to you and asks, what is the state of your environment? All you have to tell him, okay, the memory utilization on the host is 30%. This is the state of my environment. Now, if I have 2 hosts and I care about the memory of each of the hosts, then if someone comes to you and asks, okay, what is the state of the environment? I have to give 2 values, the memory on host 1 and the memory utilization on host 2. If I care about also the CPU in these 2 hosts, I need to give you, in order to describe the state of the environment, 4 metrics: the CPU and memory on host 1, the CPU and memory on host 2. So when we think about and ask ourselves, what is the state of the environment or the data center? And as I said, there are hundreds of thousands of variables that we care about to make sure that applications are getting the service that they need. A state of the environment is described in terms of those hundreds of thousands of values. So that means that when we talk about what is the state of the environment, we are talking about what we call an n-dimensional space, where each state is a vector of those hundreds of thousands of values. So if someone comes to me and I have 5,000 VMs, and I have 500 hosts, and I have 8,000 data stores, and I need to know the IOPS, the latency, and the vStorage, and the memory, and the CPU, and the ready queues, and the swapping, and the ballooning, and vStorage, and vMem, and vCPU on each of all of the. When someone asks me, what is the state of my environment, I need to give him those values for all the entities in all of those across the entire environment. So, and that's what we call an n-dimensional space. Now, what does it mean to solve this problem as it relates to a single dimension, one dimension of those hundreds of thousands of dimensions? So it turns out, and that's basic computer science, queuing theory, there is a fundamental relationship between a utilization of a resource and the delays that consumer of that resource will experience. This relationship is represented by this curve. The less the resource is utilized, the less the delays consumer of that resource will experience. As the utilization of the resource increases, delays increases. Furthermore, the slope of the curve increases as the utilization increases. This curve has what we call an asymptotic, it's an asymptotic curve, and it basically, as you get to the capacity of the resource, delays goes to infinity. And by the way, this curve, this relationship is true to anything in life. It's not just computers. If you drive through the highway in rush hour, the highway is busy, is very utilized, delays build up. At midnight, you just drive through.
Do you have trouble finding folks to be able to consume this message correctly? Because a lot of us, like the way that we go with rush hour, we figure we don't have a choice. A slow linear drop in performance just tends to be consumed as normal. And like, obviously, like I'm all about this style of delivery and this style of, you know, adaptive IT and transforming IT and how we manage it. But do you find that's one of the biggest barriers that people just say, well, you know, it's working good enough and my consumers aren't complaining, that they have trouble seeing some of that value and being able to lower that curve a little?
So I think that what's convincing users that they don't want to have degraded performance, it's actually an easy message. What's harder message, you can argue, okay, I can compromise on efficiencies because nobody will actually know that I'm spending too much money. Mm-hmm. So nobody feels comfortable saying, oh, my application is not performing well now or is suffering, because someone will complain about that. So that's an easy message. The reverse, this other side of the equation is actually harder to convince people. So now the question is, well, what does it mean to solve the problem? Is basically how far I can push to the right without getting into the red zone. Why I don't want to be in the red zone? Because when I'm getting to areas where the slope of the curve is very steep, every small fluctuation in utilization cause very small, big fluctuation in the delays that people are experiencing. So you say, okay, what's the big deal? I can solve it. How will I solve it? I'll say, okay, I don't want to get to the red zone, so I'll make sure that when I get here, I'll put a threshold, send you an alert saying, oh, you are in the red zone. But are we solving the problem by doing that? No. Because when will you get the alert? What will happen? You are already there. Performance are not assured. So you say, okay, people will say, oh, let's be proactive, predictive. Let's put the threshold a little bit to the left, to be proactively being alerted, oh, you are about to get to the red zone, basically. Okay, what do you do then? You're getting an alert, oh, you're about to get to the red zone. Okay, if you're caring about performance, what will you do? Oh, I can't take the risk, so let me figure out how to bring it to here. And let's assume you know how to do it, because it's not so simple. But what basically you accomplished? You basically moved the line of utilization to the left, sacrificed some efficiencies. You didn't run the environment as efficient as possible. And if you think about that, if you are spending $10 million on storage and compute, 1 point to the left is $100,000 that you left on the table. So even in a single variable, if I just look at one dimension of this problem that we are trying to solve, it's not so simple. It's very difficult. But remember, we are not talking about one dimension or one metric. We are talking about hundreds of thousands of metrics that have to be continuously evaluated, continuously looked at, to be able to figure out what is the state that I need the environment to be in.
But it's also like self-learning, that it's
if you hold your question in a second, I'll explain how we do it. And
of course. Yeah.
So in that n-dimensional space, what is this desired state that we want to be in or to keep the environment? So if you think about each of the dimension, so the space is this infinite set of states, possible states, as I said, this infinite combination of values for those hundreds of thousands of variables. A subset, each dimension at each layer of the IT stack defines some subsets which are good states that as it relates to that dimension. So the workload priorities and policies define some subset. The VM, vCPU, affinity, anti-affinity rules, whatever metrics we care about the VM, define some subset of states that are good states. At the hypervisor level, ready queue, ballooning define some subset of states that are good states. At the host level, CPU, memory, and so on, define some subset of state. At the storage level, latency, IOPS, storage amounts, define some subset of state. And obviously we have more and more dimensions. The desired states is a set, a small set, which is the intersection of all of those subsets. It's still a very big set, but it's a very small subset of state relative to all the possible states that the environment can be in. And solving the problem that we are looking to solve is basically figuring out at any given point of time, continuously, what is this state? What is a state that is one of those states in the desired states? And figuring out how to make sure that the environment is in one of those states. That's what it means to solve this problem. Now, how do we solve it? And that's the beauty of what we are doing. It's actually very simple. The way we solve it is that our software represents the IT environment as a marketplace. Think about anything that you have in IT, from application to the operating system, the virtual machine, virtual data center, hypervisor, hosts, storage, filers, aggregators, fabric, I/O module, switch. Regardless of what you have in IT, it's a buyer and a seller. It looks something like that, like this supply chain, where the application buys something from the virtual machines buys from the physical machine and storage, that also buys from virtual data center, the storage buys something from the disk array, the disk array buys something from the storage controller. You can go to a public cloud and the VM runs on a zone that runs on region. So there is a whole supply chain of buyers and sellers. And what do they trade, buyers, sellers? They trade commodities. Those commodities happens to be compute resources. So think about the host. The host sell memory, CPU, I/O, network, ballooning, data store, sell I/O per seconds, latency, storage amount. Virtual machine buys that and sell vMem, vCPU, vStorage. Application buys that and sell transaction per second. And I can go on and describe what's being traded in the market.
So you take that metaphor all the way into the applications inside the VM and presumably, whether you're there or not, across a group of VMs to deliver a service.
Correct.
Excellent.
Right. And by the way, it's not a metaphor. It's the algorithm. Okay. I presented several times, and every time I describe that algorithm, and then I get a question. I love this analogy. And this is not a metaphor. This is the algorithm. I'm describing you the algorithm now. And so we have a marketplace of buyers and sellers that trades compute resources. And in that marketplace, the sellers continuously price their resources as a function of the utilization of the resources. So think about the host. The host says, oh, my memory utilization is 30%. This is the price of my memory. Another host says, oh, my CPU utilization is 70%. This is my price of my CPU. The data store say, oh, my IOPS is now at 5%. This is the price of my IOPS. So the seller continuously do that. The buyers in the same time look at what they need to consume, again, based on what's being monitored, and say, okay, who can give me the best deal to what I'm consuming? So the VM says, oh, I need this amount of memory, this amount of IOPS, this amount of latency, this amount of network bandwidth. Where can I get this for the best deal? And from there, we let the invisible end of the market drive the environment to an equilibrium. An equilibrium where the supply is satisfying the demand. This equilibrium is a state in which the workload demand is being satisfied by the available compute capacity. This equilibrium is a state in which application performance are assured while the environment is utilized as efficient as possible. Now let me illustrate how this engine now deals with the typical question that you may come across on a day-to-day basis. Let's say that VMs are running and at some point an I/O bottleneck is being built up on some data store. What will happen? That data store, utilization of the I/O is increasing, prices increases, VMs that are consuming that I/O are being sensitive to that price, saying, can I get it cheaper? And if so, they'll do a storage remotion. Now, if not, what will happen? The data store will say, wait a second, I am charging those prices. I'm making much more money than what I'm spending to the aggregator. If I'm going directly to the data center, I'm making much more than what I'm making. Okay, what does a good businessman does when he sees that? He says, well, I'll open another branch. I'll clone myself. Or I'll provision more because there is the demand for my supply. That's what people do. That's what the data store will do. Later, demand goes down. Utilization goes down. Prices goes down. Suddenly, I'm not covering my cost. What does a good businessman does? He close the branch.
Make the data stores redundant.
Right? so the data stores suspend. Say, okay, I'm better off suspending, saving some money. And I can go on and go to the different things that you do on a day-to-day. If you think about that, there are 4 basic actions. If whatever the entity is out there that you really want to drive, you want to start an entity, you want to stop it when you don't need it, you want to place it properly, and you want to reconfigure it or resize it. Those are the 4 basic actions. If you kind of abstract the details, those are the 4 basic actions. And those 4 basic actions can be driven on any entity in the IT using that engine. And that's basically what we are doing. And to answer your question, the earlier question about learning, this pricing is actually encapsulate the learning. because the prices are a function of the current utilization as well as weighted with the history of the resource behavior. So when the seller price something, it encapsulates the history and the behavior of that resource. And what we deliver to the market is basically a product or a platform, a foundation, in which, using that engine, we are controlling the workload that is currently running in the environment. We are helping onboarding new workload into the environment, making the right decision of where to put it, how to start it, where to start it, when to start it, and planning for future changes of what will happen in the environment, if it will grow, projecting out 3 months, 6 months, what if things will change in the environment. Because regardless whether I'm trying to control the current workload in the environment, or I'm about to onboard workload in an hour from now, or plan for something 3 months from now, the fundamental question is the same. What is the desired state that I want the environment to be in? Or what is the state in which application performance are assured while the environment is utilized as efficient as possible? And that's what we are doing, because the engine is able us to do that, so we can do it on the things that we see now, or the things that we project will be in the environment an hour from now, 5 months from now, a year from now. And just from an architectural point of view, because I think that's very important to understand, what we have is a platform which at the core, we have an abstraction layer, which is the market. This representation of buyers and sellers in pricing and commodities. And on top of that abstraction layer, we have the analytic engine, which refer to as the economic scheduling engine, that engine where each entity makes those decisions based on prices and cost and ROIs. And underneath that abstraction, we have a very thin mediation layer that ties and maps that abstraction to whatever environments we are managing or controlling. And using that mediation, we are managing all the popular hypervisor platforms, vSphere, Hyper-V, Zen, Red Hat, all the cloud orchestration like VCD, Cloud Stack, we are adding OpenStack. Using WMI, JMX, SNMP, looking into the guest OS, talking to the fabric, managing the fabric by talking to UCS Manager, talking to the backend storage, talking to NetApp Manager and other element managers in the storage. But the key here, that what this mediation gives us is a mapping of whatever we want, whatever we need in the market in order to know about the environment, as well taking advantage of all the control knobs that are exposed in software by those elements, and everything above it stays the same. So when you take our software, you have one instance of our software to manage whatever you have in your environment, heterogeneous, all kind of platforms. With one instance of the software, you get a semantically integrated management for your entire IT stack across heterogeneous environments. And what we deliver to the market is basically using that foundation, different control modules for the layers of the IT stack, from the application all the way down to storage and hybrid cloud, and we have plug-in to the different environments that we are managing. Any questions on the technology?
I guess we'll probably get into a bit more later on the hypervisor support. You talked about OpenStack. Is it OpenStack layered on top of Zen, or do you have is KVM in your roadmap or in the plans right now? Obviously, you cover the major players with vCloud with vSphere and with Hyper-V and Zen. That's a I see you've got RHEV on there.
Right.
But given that RHEV is moving away from their stuff into their OpenStack platform based on KVM.
So OpenStack and KVM is going to be released in Q2 of this year.
Oh, great!
Actually, I'll take it back in August 1st. August 1st, which is we call it the Q2
We'll
release.
edit that out in post. It's all good.
What?
We'll edit that out.
You want to talk about John? About the